We want to find the field between these two particles. One's a proton and the other is two protons. And we're given the distance by which they're separated. And we're interested in the field right in the middle. And field is E. We just saw an equation for field. And we've seen that the total field at a point is the sum of all the fields from all the different point charges. So we're going to have to add up the field from this point charge and this point charge. Now let's look at this one first because it's bigger, our alpha particle. So it's creating a field. Well, which direction would the field be in? Which direction would a positive chest charge feel a force? It would be repelled from a like positive charge here. So the alpha particle is creating a field in this direction. And direction is important to consider because field is a vector. So looking at the alpha particle, here is our kq over r squared. K is this. Q is 2 times the charge on a proton. And the distance is the distance between that particle and the point at which the field is being created. So that is not the distance between the two particles, it's the half of the distance between the two particles. I mean, we could just, plug in 910 nanometers, but then we'd be finding the field at this point all the way at the other particle. And I'm converting that into SI units of meters and remembering to square. So now we have to add the field that's created by the one proton on the left. And is it really adding? It would actually be more of a subtraction because the proton's on the other side and it's pushing a positive particle here in the other direction, so it's creating a field in the other direction. So if we're assuming that left is our positive direction, this is a negative field. And the kq over r squared is going to look very similar. So all this stuff here, I just copied it and I'm going to paste it. And we're subtracting it because it's in the opposite direction, and we're making one other change. The charge isn't 2 times 1.6, it's just one of them. And when we do the subtraction, we get this. So in effect, we can think of it as something happening like this. The proton is canceling out half of the field that the alpha particle makes. So the overall field, instead of being, just that from the alpha particle, is exactly half of what it would have been if the proton hadn't been here. So that's what the actual overall field looks like. And when you run the numbers on your calculator, you should get a result like this: 6.95 times 10 to the third newtons per coulomb. Now I figure I'll just help you get started on a similar question. What's the field at the midpoint between a proton and an electron? So the same principles and equations apply here. We just have different charges, maybe a different distance between them. And a different direction of the field from the electron. So think if we put a positive test charge here, it's going to feel a force toward the electron because of the electron's charge. Opposites attract. So it would also feel a charge away from the proton because like charges repel. So the sum of the fields from the proton and the electron is going to look like this. And since the magnitude of the charges are equal, we'll let Q stand for that 1.6 times 10 to the negative 19th Coulomb charge. We can express the total field like this: 2 times kq over r squared. And again, r here is half the distance between the two particles, the distance between any one particle and the midpoint.